Look up at the power lines running down your street and count the wires actually carrying electricity. Almost anywhere in the world, the answer is 3. Look at one of the big steel transmission towers marching across open country, and you might count 6 or 9, but look closer, and they're always arranged in groups of 3. 3, not 1, not 2, not 10. And here's the strange part. Your entire house runs on essentially just one of those 3 wires. That number, 3, is one of the most important design decisions in the history of electricity, and almost nobody ever notices it. So why 3? The answer starts with a problem that a single wire simply cannot solve. Start with what a single AC circuit actually does. The voltage doesn't sit still. It swings from positive, down through 0, to negative, and back, 60 complete cycles every second. That's what 60 Hz means. Now, the power being delivered is voltage times current. And when the voltage swings through 0, so does the power, twice in every cycle. So a single-phase circuit doesn't deliver a smooth, steady stream of power at all. It delivers pulses, surging up to a peak, then dropping all the way to nothing, 120 times every second. You've actually seen this with your own eyes. An old fluorescent tube flickers because its brightness rises and falls 120 times a second, tracking those power pulses. Your eyes are too slow to catch it, so it looks steady. For a light bulb, that's completely fine. But now try to run a motor on that pulsing power. Every pulse is a kick of torque, and every gap between pulses is a moment of nothing. The motor shudders, hums, and hammers on itself. Lumpy power is a genuine engineering problem, and the fix turns out to be beautifully simple. Don't use one AC circuit. Use 3. Generate all 3 from the same machine, at the same 60 Hz, but stagger them in time, so each one is shifted by 1/3 of a cycle relative to the next. In electrical terms, 120 degrees apart. Now watch what happens at any single instant. When the first wave is passing through 0, delivering nothing, the other 2 are up near their peaks, carrying the load. There is never a single moment when all 3 sit at 0 together. They take turns. And here's the payoff. Add up the instantaneous power of all 3, moment by moment, and the pulsations cancel out completely. The dip in any one phase is filled in, exactly, by the other 2. The total power delivered by 3 staggered waves is dead constant, as smooth and flat as a battery, even though it's built out of 3 sources that are each pulsing wildly. That alone would justify the whole system. But 3-phase has a second gift, and it's the one that actually built the modern world. Arrange 3 coils of wire in a circle, spaced evenly around it, and feed each coil one of the 3 staggered phases. Each coil produces a magnetic field that grows and shrinks along with its own wave. But because the 3 waves peak one after another around the circle, the combined magnetic field doesn't just pulse in place. It sweeps around, a smoothly rotating magnetic field, turning around the circle 60 times a second in the simplest machine, and created with no moving parts at all. Now drop a plain metal cylinder into the middle of that spinning field. The rotating magnetism drags it along, and it begins to turn, chasing the field around. That is an induction motor. No brushes, no contacts, no starting crank, just 3 wires and a lump of metal. This was Nikola Tesla's insight in the late 1880s, and it is not an exaggeration to say it powers civilization. Nearly every industrial motor, every air conditioner compressor, every pump, elevator, and factory conveyor, and the drive motor in most electric cars, is a descendant of that spinning 3-phase field. So why exactly 3? Why not 2 staggered waves, or 4, or 10? This is where the engineering gets ruthless. 1 phase can't make a rotating field at all, and it's power pulses. 2 phases can make a rotating field, but the combined power still pulses, and you need 4 wires to carry it. 3 phases is the very first arrangement that gives you both things at once: perfectly constant power and a clean rotating field. And then comes the detail that sealed it. In a balanced 3-phase system, The three currents always add up to exactly zero at every instant, which means they can share a circuit with no dedicated return wire at all. 3 wires do the job that would otherwise take 6. Going beyond 3, 6 phases, 12 phases, buys you almost nothing extra, while every added phase is one more wire, one more conductor, more copper hanging in the air. 3 is the exact point where you get everything that matters and pay the least for it. It's an optimum, not a tradition. So where does all of this actually live? Everywhere between the power plant and your neighborhood. The generator at the plant is wound in 3 phases. The high-voltage lines striding across the country carry 3. The entire bulk grid is 3-phase, end-to-end. Then, at the transformer on the pole outside your neighborhood, something quiet happens. The grid hands your house just one of the 3 phases, split into the 240 and 120 volts sitting in your panel. That's why your dryer and your oven get 240, and your phone charger gets 120, all off that same single phase. A factory or a large office building is different. It takes all 3 phases directly, because it's full of the motors that 3-phase was invented to run. And this basic split has barely changed in over a century. The first long-distance 3-phase line ran 175 kilometers from Laufen to Frankfurt back in 1891, 3-phase, about 75% efficient, and the fundamental design has been right ever since. So the next time you look up at those 3 wires, you'll know they aren't 3 copies of the same thing. They're 3 separate ways, but that entire arrangement rests on one fragile assumption. All 3 phases have to stay perfectly balanced, and exactly a third of a cycle apart. In step, always. When they slip out of balance, when one phase sags, or the timing drifts, the constant power turns lumpy again, motors start to overheat, and the rotating field begins to wobble. The steadiness you take completely for granted is 3 waves holding a formation. What happens when that formation breaks is a failure the grid works every single second to prevent and very rarely gets to talk about.